Hi, I'm Frank. I'm from China, and I'll be coming to Cambridge for my PhD in October. This speech was actually recorded in advance because I'm still in China and I need to use a VPN to access Zoom. And the VPN can be a bit unstable, so maybe audio chatting is okay, but sharing my screen and switching slides might be super laggy. So I thought it would be a good idea to just record in my presentation beforehand. Since last July, I've been working with Kashif and Amelia to develop an app for measuring tree trunk diameters. We've already submitted a paper on this work, so a lot of this talk will cover that paper. Earlier this year, we started a new project, so I will also spend some time talking about what we are working on. I won't follow our paper structure exactly, otherwise it would be too boring. So just skip some tedious parts, but this shouldn't detract from your overall grasp of what we did. Also, I think I should be there in the meeting room when this video is played, so just please feel free to post any questions in the chat, and I'll respond each of them in time. Okay, without further ado, let's get started. Um, in forestry, we typically measure the diameter of the trunk at 1.3 meters above the ground, and this diameter is called dBH. The first important question is why do we need to measure the trunk diameter? And the answer is dBH is an important indicator. First, by measuring the trunk diameter, we can monitor the growth and health of the tree, and it's also widely used in forest management and planning, where trunk diameter data can optimize logging and planting plans. Another important use is that a dBH can be input into allometric equations to calculate carbon storage, which is significant for carbon emissions and carbon credit. Lastly, different species and size of trees support different biological communities. So DBH is also used by ecologists to access biodiversity. Next, let's talk about some common methods for measuring trunk diameters. The first is the conventional method, which is manual measurement. This usually involves using a tape measure or a caliper. Obviously, it's very simple, but its biggest drawback is that it's very time consuming and labor intensive. Therefore, in recent years, terrestrial laser scanning has been widely used in large scale forest measurement. It uses ground based LiDAR to generate high density point clouds for forest analysis. But the device is very expensive, so it's only accessible to those best funded organizations. And airborne laser scanning is also a common method. By deploying LiDAR on aircrafts, ALS can capture large scale forest data. However, a significant issue is that aircraft usually fly above the canopy, right? And when the forest is too dense, the beam from the LiDAR can hardly penetrate the dense canopy, and this will pose challenges for dBH measurement. And currently, there are also studies using mobile laser scanning for diameter measurement. This method is highly customizable. For example, if you look at the three pictures here, they're using LiDAR on a backpack, and handheld device, and vehicle respectively. So due to its high customizability, MLS can also collect parameters such as tree height and trunk volume. But still, since this method uses point clouds, a lot of time is required for post processing on a powerful computer. In recent years, drones have also been used for forest scanning to measure dBH. Here, I think it's necessary to distinguish between UAV-based method and ALS. So, from my understanding, the UAV method are usually conducted under the forest canopy, while ALS is usually above the canopy. For instance, a study from the University of Pennsylvania proposed a dBH measurement method using drone with an automatic obstacle avoidance system. And the advantage of using drone is that they're not very costly. and they are also very flexible. But since UAV flights under the forest canopy, right? So they can be affected by wind or dense foliage sometimes. Now here comes the focus of our study, which is smartphone-based tree trunk diameter measurement solutions. This table is actually from our paper, and it shows that smartphone-based solutions are not actually something new, but several knowledge gaps still exist. The first is the high device equipment. Most studies require smartphones to be equipped with LiDAR or time-of-flight cameras to obtain dense point clouds or high-quality depth images. And the second thing is that many related work overlook common situations in forest environments, such as occlusion or leaning trees. The third is that since some methods use point clouds to estimate the trunk diameter, they often require the operator to walk around the trunk to get the point clouds. But this can be very tricky in some dense vegetation. Lastly, if like point clouds are used to estimate the DBH, processing point clouds on a smartphone can also be a problem when it comes to computational cost. Therefore, many methods still opt to export data to a computer for post-processing, so they do not support real-time in-field measurement. And our research aims to fill these knowledge gaps. Okay, in fact, I'm not the first student to work on this tree diameter project, so my work is largely built on the work of the previous team members. The first student should be Amelia, who was pursuing her master's degrees at University of Waterloo at that time. And here I show her master's thesis, where she proposed a method that only requires taking pictures of the trunk from one side and to get the trunk diameter. Also, she took into account like factors that would potentially affect DBH estimation, such as occlusion. And then in 2022, another student of Kashev named Sofia introduced UNet for trunk segmentation in her master's thesis. In 2023, Amelia organized her work during her master's and published the paper in remote sensing. In her work, she used pure image processing algorithms, so there's no deep learning, and she used a Huawei phone with a time-of-flight camera to obtain the depth information through Huawei AR engine. And then in July 2023, I graduated from undergrad school and started working with Amelia and Kashev to improve this project. I think the keywords here are DNN-assisted segmentation, because I trained a neural network to segment tree trunks. We also switched the AR platform from Huawei AR Engine to Google AR Core, making the app compatible with most Android phones. We named the app GreenLens and open sourced our project. And this January, I started developing GreenLens 2, and I'm right now collaborating with Yihang, who is also working on Unreal Engine and deep learning. Okay, that's basically everything about how this work involves. Let's move on to the methodology. As I mentioned earlier, my work largely builds on Amelia's work, so I would just introduce our image processing pipeline through a comparison. And let me just first introduce the image processing pipeline proposed by Amelia. So first, Amelia used Huawei AR Engine to obtain high quality depth images. You might wonder that like the depth image here doesn't seem to be very high quality, but I can assure you that you will change your mind after seeing the depth images from Google AR Core. The first step in her work is called filtering, where the algorithm first finds the trunk's depth value, which is delta, and then retains only the pixels that have a depth value below or above 10% of delta. Then, Amelia used a convex hull algorithm to determine which pixel clusters belongs to the trunk. This algorithm is a bit complex, so I will not go into the details to time constraints. But this should not affect understanding the whole process. And then the trunk is rotated until it is vertical. Then The trunk's boundaries can be fitted with two straight lines. Amelia then constructed a pinhole camera model to calculate the trunk diameter. Here, gamma is the camera's focal length, and delta is the distance between camera and trunk, which we can get from the depth image. And D here is the trunk width in the image, or the distance between the two parallel lines in pixels. And finally, the original RGB image with the detected boundaries is displayed on the UI for user inspection. And if the user finds any issue, they can just recapture it, or they can then all these processes are performed all over again. Okay, now I think it's the time to talk about what we did. Let me just first introduce Google AR Core. It's another AR platform, but uses a depth from motion algorithm to perceive depth information from an optical camera. So without needing a specialized depth sensor. Depth from motion is essentially based on structure from motion, as shown in this image, by moving the camera, taking multiple photos of some feature points in space from different angles. The position of these feature points can be reconstructed, and these feature points, after interpolation and smoothing, can finally form an AR core depth map. Okay, next let me introduce the data we used. Here I highlight the word coarse because, as you can see, the quality of AR depth images is much lower compared to that of AR engine. So I think a major challenge in this project is identifying the trunk and measuring the trunk diameter with such poor quality depth images. And also, what makes things even more challenging is that the ambition that we want to take measurements even when the trunk is not fully visible. So to address the problem where the trunk might be occluded, we introduced a step called RGB filtering. The motivation is that we noticed that in forest environments, occlusion is often caused by foliage, lianas, and low shrubs, and in most of the cases they're green. So therefore, we just design a process to exclude green pixels and retain the brown pixels, since trunks are usually brown. And to do this, we first convert the RGB space to HSV space, which is more suitable for color processing, and then we exclude green HSV values and retain the brown pixels. And so finally we get a image like C here in the flowchart. I think a key question is how can we determine green and brown HSV values? Here I just take brown as an example. The process is we segment some typical trunks and extract the HSV values of each pixel and send all these values to a k-means classifier. Then we can get 100 HSV values corresponding to brown. And also there might be a few colors that are very close to green. We just exclude them. And I guess some might ask, what if the trunk is green? But don't worry, we just found that the neural network in the pipeline, which I'll talk about later, has very good ability to generalize. So the app can still identify boundaries even if the trunk is totally green. After RGB filtering, we proceed with depth filtering. So this step is pretty similar to that in Amelia's work. We first use image C, which is the result of RGB filtering, as a mask on the original depth image, and that is image D here. Similar to Amelia's strategy, we would only retain pixels that have a depth value above and below 10% of the trunk steps. Lastly, we just enhance this filtered depth image. The algorithm for enhancement is a bit complicated, so I will not just go into the details here. All we have to know is that the enhanced depth image can better represent the trunk. And then to know where exactly the trunk is, we then perform trunk segmentation using a neural network called BBSNet. It has two ResNet50 backbones to extract RGB and depth features. As shown in the flowchart above, it takes two inputs. One is the enhanced depth image, and the other is the original RGB image. So let's take a closer look at the architecture of the BBSnet. It's also a bit complex, so I just keep it simple. It starts with RGB and depth images, which go through two Resonate 50 modules to get the RGB and depth features. These features are then fused together and then decoded to get S1. And if you look at S1, you'll see it's kind of like a rough mask. And this mask is then sent back to enhance those low-level features. And finally, we decode it again, and to get S2. S2 would be the final output of the model. Because some trunks are leaning, right? So we use the method from Amelia's paper to adjust their orientation to make them upright. Here we use principal component analysis, PCA, by finding the main axis of all the pixels in the image plane, and we then rotated the main axis until it's perpendicular to the frame bottom. Okay, now the trunks are upright. We can just determine their boundaries. Here we also tried two other methods for fitting the boundaries. First, we use two non-parallel lines, and then we tried using like curves as the trunk boundaries. But we didn't really adopt these two methods. Let me just explain why. For the non-parallel line fitting, we compared it with the parallel line. Specifically, we used bootstrap sampling and repeated the experiment 1,000 times and got results shown in this table. The values in the table represent the 95% confidence intervals. So we just found that the parallel line method has smaller errors in terms of diameter estimation. And for curve fitting, we found that it wasn't very robust in cases where the trunks are occluded. So as a result, we just stick with the initial fitting method using two parallel lines to ensure robustness in various measurement environments. And after determining the trunk boundaries, we also modified the diameter calculation formula. We built a pinhole camera model as shown in the figure. But due to the parallax effect, the real diameter of the trunk, which is PQ in this figure, is not projected onto the image plane. So instead, it's actually AB that gets projected onto the image plane. And by using the similarity of triangles SBO and SHB1, we got an equation like this. And after simplifying it, we got the final diameter calculation formula. Okay, lastly, we displayed the identified boundaries and diameter estimate on the UI. But sometimes the app gives incorrect lines, right? So to handle this, we added a feature for manual adjustment. So right now, besides retaking the photo when the result is incorrect, users can also manually adjust the lines until they are satisfied or until these lines are perfectly aligned with the trunk edges. Okay, let's move on to the results. So first, our main concern is accuracy. We collected 362 samples from urban, peri-urban, and forested environment for evaluation. We found that the predicted diameter aligned well with the ground truth dBH with an R square of 0.97. But if we took a look at the red boxes in the two graphs, we can see that the error is significant when the trunks are very large. For example, in the right graph, the median error of for trunks with dBH larger than 80 centimeters is almost close to 10 centimeters. So we just tried removing these large trunks and found that the RMSE decreases by almost 2 centimeters. So right now, when the app measures a trunk whose diameter is greater than 80 centimeters, it will just suggest the user to do a manual measurement because the app-based estimation might be distrusted. And we also compared our method with other smartphone-based studies. We found that our solution has 4 big yes and our error is comparable to those studies using high-end smartphones. Okay, let's just move on. And also we analyzed the sources of error using ordinary least squares regression. First, we rule out multicollinearity through a Pearson's test. No apparent linear correlation was found between the different variables, so it's safe to do an OLS regression. Here is the regression result, and the coefficients indicate the contribution of each factor to the overall estimation error. We found that extreme occlusion has the largest error contribution. It's about 3 centimeters. Then its irregular shapes typically introduce an error of 1.23 centimeters. But for other factors, we didn't really observe like significant contributions, which might suggest that our method is robust in these cases. Okay, next we design an experiment based on the ablation test. So ablation testing is mainly used in the computer vision field, where different modules are gradually removed from the model to observe the effect of each module on the overall accuracy. I assume you still remember this flowchart, right? Here we selected 4 modules for testing. They're RGB filtering, rough depth filtering, depth in image enhancement, and inference result enhancement. We also set up a vanilla model, which means feeding the raw RGB and depth images directly to the neural network without any pre or post processing. Here are the results of the ablation tests. Each row in the table represents a test scenario and its error in terms of diameter estimation, and the image below here shows the RGB image and its corresponding predicted mask under different test scenarios. So let's first look at the table above here. Like we can see that these modules are gradually added. When these modules are gradually added to the model, the overall estimation error would decrease, right? And also I want to highlight scenario 4 and 5 because they can reflect the important role of RGB filtering. Also, if we look at the visual results of this ablation test down here, RGB filtering makes the output from the neural network more accurate, therefore, improving the accuracy of the diameter estimation. All right, that's basically about everything about our previous work. So let me just take some time to talk about the work we are currently working on, which I believe is more interesting. First, we aim to address some of the shortcomings of our previous work. For example, in GreenLens 1, we could only measure one tree at a time, but in our new work, we aim to measure multiple trees simultaneously. The second thing we want to improve is to predict the DBH directly from the neural network without, doing additional calculations. This is also called end-to-end DBH prediction. The third point is that we're going to redesign the app's UI and to make it more interactive and user-friendly. Here is the flowchart of GreenLens 2. The orange modules are related to the app UI, which I will showcase later. So here I just want to talk in detail about the 2 blue modules here because they involve the core algorithms. First is trunk detection. Like we use the YOLO V8 nano model to get the bounding boxes of the multiple trunks from camera frames in real time, and then we use some common neural networks backbones like ResNet 50 to extract features from the RGB and depth images and fuse these features together. So right now we've got the bounding boxes, right? And also, so the next thing we do is to only extract features within these boxes. And these extracted features are then sent to a neural network called DBHNet, which is a multitask network. The first task is instant segmentation, which segments each trunk within the bounding boxes. And the second task is end-to-end diameter prediction. We use the mask to extract the relevant depth features, and these features go through some fully connected layers to get the predicted diameter. But the whole process is actually more complex. So this is only a simplified version. Here I'm showing a more detailed flow chart, and also it looks a bit complicated, but I'll demonstrate the app in a minute, so which should be more intuitive than just staring at this flow chart. So let's just skip this for now. All right. Now I think we're going to the most we are getting to the most interesting part of this work. Remember, we want to perform end-to-end DBH estimation, right? Meaning that the neural network will directly output the trunk diameter. To do this, we need a large amount of data with images and annotations to train the neural network. But the thing is, collecting data in the real world is very time consuming. So we are considering if there's a simpler way to collect tons of data for training the model. Of course, the answer is yes, and we can do this by using Unreal Engine. Here I have built a virtual game scene that currently includes 250 trees featuring 10 different species, I think, and each trunk has different diameters, and many parameters in this game scene are actually customizable, such as the camera's pose and position and the shapes of the tree, the weather, and the lighting. So by tweaking these parameters, we can generate an unlimited amount of photorealistic data. But besides building the game scene, we also need a simulator to obtain the multimodal data from the Unreal Engine. And our current raw dataset includes 4 modalities: RGB, segmentation, depth images, and point clouds. So these raw dataset have great potential in scalability. And next, I'll show you how to expand this raw dataset to get new data. We need to predict the trunk diameters, right? So we actually prefer to get masks of just the trunk section rather than the whole trees. In this case, we can use an additional image processing pipeline to get the trunk masks. Here, I used some classical image processing algorithms along with segment anything model. It's a large model for segmentation tasks. So by running this pipeline, we will have the trunk masks, right? But we still need the ground truth diameters because we want to do a diameter estimation. But getting the trunk diameter is also very straightforward in Unreal Engine, because we can just manually measure the diameters in the game scene. I think that's the simplest way to go. Or we can just write a program to get this data automatically. Okay, finally, let me just talk about our new app, GreenLens 2. We used Flutter as the framework to develop the whole to develop the entire app, because it has good cross-platform capabilities, which allows us to develop both Android and iOS apps. So for the AR platform, we use AR Core on Android and Apple's ARKit on iOS. For the on-device real-time trunk segmentation, actually YOLO Teams provides Flutter code for mobile devices, so we just need make some minor modifications to use it. And also, because we need to perform on-device neural network inference, we plan to use PyTorch Mobile on Android and TensorFlow Lite on iOS. Okay, the founder of the Linux once said, "Talk is cheap, show me the code." So let's just launch the Android Studio and fire up an app demo. But the app is still under development, so actually many windows or many features are just using static images, and there are many features that haven't been implemented yet, but they should roll out before I come to Cambridge. Okay, here I've already launched the Android Studio, and this is a GreenLens 2 project, and you can see this is a Flutter project. And like I mentioned before, it has very good cross-platform capability, so we can actually develop Android app inside here, and also there is also iOS app. So as a demo video, I just show you how like Green is to run on an iPhone. So let me just turn on the simulator, and this is a iPhone 14 Pro Max, and yes, actually you can run iPhone inside Android Studio. So I've already launched the GreenLens 2 app, and you can see this is a home page, which is essentially like a dashboard. This is a summary of the user collection, tell you how many plots you've created or how many trunks you've collected. The second panel here is the recent plot, which I'll talk about in detail later. And the third panel, there's a support check. For instance, if you're using iPhone 14 Pro Max, so there's a LiDAR on this device. So there's a message box to the user that your device is equipped with LiDAR, which allows for more accurate measurements. And below here, there's a map. So when users are trying to measure the tree diameters, the app will not only record will not only predict the diameter, but also like record where you collected the data. So you will show a map like this. But as I mentioned before, so this image is actually a static image because this feature isn't implemented. Okay, let's just click on this recent plot and see what's are there. Okay, this is the information about plot 1, and you can see this is where you collected the data, although there are static images. And there's a summary, and this is an inventory. So right now I've already created a one. This is sync 1. There are 3 trunks included. So let me just show you by adding another one. Let's just click the button here. This is actually displayed in landscape mode, so let me just rotate the device. Okay, let's just take a look at the center window, which is the largest window here. And you can see this is a camera preview, and there are a lot of colored bounding boxes. And also on the upper right side, there is a depth image panel. So when the user is trying to moving the camera, these previews will be updated in real time, and all these bounding boxes will be rendered on this UI as well, on this page as well. Okay, so if you think that this is okay, then we just click this button, and this will go into another page for inspection. Let me just turn into portrait mode. Okay. Okay, so this is actually a result inspection page. So you can see we got the RGB depth image shown here, and also there are some bounding boxes that have been detected. As you can see, there are actually 5 boxes. 3 of them are at the center of the image, and there are actually 2 bounding boxes that are being excluded. The reason is that for this yellow box, it says part of the trunk is outside the frame. So in this case, it's you don't have to really measure that because the result would be incorrect. And for this orange box, it says it's 6 meters away from the camera, which is we just found that. So when the trunk is 60 meters away from the camera, then the estimation isn't very accurate. So we got 3 bounding boxes here, which is there are this red, blue, and green one, and we can always edit them or remove them if necessary. And also there are some cases where maybe some trunks are not detected, and if you want to measure them, you can just click this button here by adding them manually. Okay, I think it looks good for me, so let's just confirm. And let's just wait for a second because okay, so right now we got the estimate DBH, and also we can see here that this is a segmentation result of this trunk, and as you can see, I think it's very accurate, so there's no need to remove them. But if you found if the user find it's not very accurate, it's completely wrong, then you can just choose to remove these trunks. So for me, I think it looks okay. and let's just click confirm. Okay, then we're back to the plot page. But the figures here are not updated because I haven't really make it dynamic. But I think I should do this later. But I think so this is the overall user journey of this app. I was planning to put an end to the presentation today, but I just found that I still got some time left. So here I'm going to show you, the whole virtual forest thing in Unreal Engine because I didn't really make it very clear in my slides about how we make this happen. So I already opened up this Unreal Engine editor and this Unreal Engine 5, and you can see this is the game level editor where you can just select this different asset inside this game level. And on the right side, there is a panel which is a overview of all the assets here in this game engine. Like I mentioned before, there are exactly 250 trunks in this game level. But you can actually make it more if you have better GPU. Like for instance, if you got a 4090, then you can make it to maybe 300 or even 500. So I think one thing interesting about the Unreal Engine is that you can actually customize a lot of factors inside this virtual scene. For instance, I'm right now selecting a trunk, right? It's just selected, and you can see there are a lot of attributes here which are editable. So let's just try to make it even bigger. Like we change from 0.8 to 1.5 perhaps. Okay, so right now you can see this trunk is becoming bigger. Let's just undo this because I just want to. Okay. And another interesting is about the weather system in this game level, because here I use the Ultra Dynamics Weather. It's a plugin from Unreal Marketplace, and let me just show you what is this dynamic weather capable of. So right now we're choosing a weather type as clear skies, but we can actually change it to maybe to snow blizzard. Okay, you can see like right now it's snowing right now, and also the ground is piled up with the snow, right? Let's just maybe switch back to undo all this. Okay, back to the clear sky. Right. Okay, I think another key question is that right now we already got this photorealistic forests, virtual forest, right? But we want to get RGB images and depth images or some segmentation images from this game scene. So how can we make that happen? So we do this by using a simulator called um, Colosseum. So it's a GitHub repository for Colosseum, and it says it's a successor of AirSim. So AirSim is essentially a simulator for drones, cars, and more built on Unreal Engine. So by tapping into Colosseum, we can get these images from the Unreal Engine. So let me just show you how we did this. Here we have to activate the game scene, and you can see, okay, right now the game level is activated. And maybe you can notice that there are 3 sub windows down here. There are RGB, depth, segmentations, images respectively, right? And we can just manually remove the camera by using the keyboard. So actually we can also automate all this because we don't really want to flying through this forest using the keyboard. So we can do this by using some Python script. Here I just show you how to do this. So here, this is a Python script that I wrote for just collecting all the data from the game scene automatically. So let's just kill this process. Okay, let's just play. Let's just start this program, and let's back to this game scene. You can see, okay, the scene just changed automatically, and the camera will just transport from one place to another place, right? And you can see here, okay, it's snowing right now because this weather system is totally automatic. Okay, it's changing right now. Okay, I'm just here, and also we just change it from we just generate some images from the Unreal Engine, right? And we can check that if they are Okay, they are generated here you can see here there are two images just generated, and there are also depth images. So this is depth PFM files, and also this is a segmentation, right? Okay, so it seems like everything is fine. Okay, that's basically about everything about Unreal. Okay, great. That is the end of my presentation, and thanks for listening. If you have any questions, just please feel free to ask.